At the end of World War II, the Allies captured a number of German V-2 rockets. This prompted British fiction writer Arthur C. Clarke to suggest that these weapons be used for a more peaceful purpose: artificial satellites. He proposed that 3 such satellites be positioned around the Earth to enable worldwide communication. The creation of such satellites was facilitated by the recent invention of the transistor, solar cell, and the traveling wave tube. The biggest obstacle, however, was the inability of contemporary rockets to launch the satellites into orbit. This problem was only solved by the invention of the ICBM at the height of the Cold War in the mid-60s, with the United States launching the first commercial satellite, Intelsat-1, shown here in the picture, and the USSR rapidly following suit the same year. Despite these rapid technological advancements, it would take another decade for satellite communications to become commercially viable, and it was not until the 90s that they saw widespread liberalization for civilians. Satellite telecommunications depend on 3 major segments: the ground, space, and control components. When data is sent through the satellite network, the data is first modulated onto a carrier frequency by a transceiver and sent to the satellite by an antenna on the ground. When the satellite receives this transmission, its transponder amplifies it to avoid signal degradation and data corruption, since we know that these signals need to travel really long distances through the atmosphere. The signal is then shifted to a predetermined frequency to avoid interference between uplink and downlink signals, and then the signal is retransmitted back to Earth and received by stations on the ground, which demodulate and process the signal into the data that was originally sent. The control center on the ground ensures the smooth operation of this whole process. And since multiple users need to be served simultaneously, satellite network providers employ techniques such as time division and frequency division to allocate resources equitably and efficiently among their users.
The image illustrates satellite networking across 3 orbits: low Earth orbit, medium Earth orbit, and geostationary orbit. It highlights the significant latency differences and clusters based on altitude. LEO and MEO satellites are in motion, providing faster, flexible coverage, while geostationary orbit remains static for consistent global communication. Low Earth orbit satellites at altitudes of 500 to 2,000 kilometers complete an orbit in 1.8 hours, enabling low latency communication. Using laser inter-satellite links, they create mesh network, reducing ground station reliance and enhancing global connectivity. Software-defined satellite networks optimize bandwidth and multicast for growing video sharing demands. The software-defined satellite network architecture features a control layer of LEO satellites for network management, a data layer for forwarding data, and an application layer for reduced redundancy. Unlike terrestrial networks, software-defined satellite networks faces challenges like satellite weight and power limits. Power distribution is optimized using AI. Medium Earth orbit satellites orbiting at 2,000 to 35 kilometers offer lower latency than geostationary satellites while covering larger areas than lower Earth orbit satellites, making them ideal for global mobile communication, GPS, and broadband. The diagram illustrates the Walker constellations, which optimize coverage. Dynamic techniques ensure efficient, low-latency data transmission. MEO satellites balance performance with moderate maintenance challenges. SpaceX, Starlink, and OneWeb are the 2 major satellite operators. They operate LEO satellite constellations, with Starlink's 7,000 satellites at low altitude, offering reduced latency. Starlink uses laser inter-satellite links for a mesh network, therefore minimizing ground station reliance. In contrast, OneWeb, with fewer higher altitude satellites, depends more on ground gateways, increasing latency but achieving broader coverage per satellite.
Now that we have introduced you to satellite networks and that you have a better idea on how they work, you should be asking yourselves the question, why does all of this matter? In the following minutes, I will present to you some insight on the benefits and opportunities involved with the use of satellite networks. Let's start with the first point. The Internet of Things, if you are unfamiliar with the term, basically refers to the collective network of connected devices and all the technology that allows them to communicate and exchange data with each other and other systems over the Internet. Over the past decade, it has expanded significantly, being applied through massive wireless sensor networks in smart cities, transport, remote agriculture, and offshore monitoring. These applications have been successful so far, but future uses will require connectivity in rural and remote regions. One of the main advantages of satellite internet over traditional internet is the large range of regions that it can reach. As satellites don't require terrestrial infrastructure to transmit data, they can support connections to the most remote places on the planet, like rural or maritime areas that would otherwise be hard to reach with traditional broadband options like fiber or cables. This flexibility, as we can see here, can benefit multiple industries and will become increasingly important as exponentially more devices get connected through the Internet of Things. Fields like resource management, including solar energy, oil and gas extraction, and many others such as environment monitoring, mining, etc., will need the operation of the Internet of Things in remote regions. Additionally, leveraging satellite internet through low Earth orbit constellations could provide fast and reliable wireless connectivity in high-speed moving platforms. For example, it could allow for in-cabin internet access on airplanes and high-speed trains through satellite communication links.
While satellite internet has many advantages compared to other forms of internet, it also comes with important challenges that impact its overall effectiveness. One of these is latency, which is a delay often caused by the long distance data must travel, which can go up to 36,000 kilometers to and from the satellites in orbit. Latency significantly affects the quality of service, especially in applications that need real-time interactions like streaming or video games. Efforts to mitigate this include technologies like mobile edge computing, or MEC, which processes data closer to users. MEC not only reduces latency, but also enhances consistency, which makes satellite internet more viable in urban areas where real-time connection is important to users. Another limitation of satellite networks is the need for a clear line of sight between the satellite and the user's dish. Obstructions like buildings, trees, or even water can weaken signals. Adverse weather conditions, such as heavy rain or strong winds, exacerbate this problem, often rendering connections unreliable. Solutions to this problem involve using higher frequency bands, such as the Ka band, which improve bandwidth but remain vulnerable to obstructions. Alignment tools like SAT finders can also help ensure optimal dish positioning and maximize signal strength. Security is another significant concern. Satellites have limited computing capacity, which restricts their ability to use advanced encryption protocols, making them vulnerable to data breaches. Furthermore, since a single satellite typically serves a very large number of users, this increases the risk of large-scale cyber attacks that could compromise entire networks. To address these challenges, stronger encryption and enhanced authentication methods are essential. Ensuring the safety of satellite networks is critical as they handle increasingly sensitive data in today's interconnected world. In summary, while satellite internet offers unparalleled coverage and serves as a lifeline in remote and emergency scenarios, its limitations are clear. However, innovation is inevitable, and competition for better latency, reduced cost, and improved reliability means satellite internet is assured to continue its evolution and become a truly global telecommunications technology within the next few decades.